For over 100 years, architects have waged a constant battle against gravity. City skylines became proving grounds, pushing columns of steel and concrete ever higher into the atmosphere. Then, in 2004, a proposal emerged from Dubai with a target that broke the scale entirely, a structure stretching a full half-mile into the sky. A building so massive that you could watch the sunset from the ground floor, take an elevator to the peak, and watch the exact same sunset all over again. Reaching that altitude meant exposing the structure to brutal environmental extremes. The tower would have to withstand hurricane-force winds tearing across its upper levels, all while baking in blistering 120-degree heat. But before a single steel beam went up, engineers faced a geographical flaw that threatened the entire project. They were trying to place the heaviest building on Earth directly onto loose, shifting desert sand. Dubai was racing against time to pivot its economy away from oil and toward global tourism. To do that, the government needed an instantly recognizable icon, and developer MR Properties stepped up to finance the risk. Before MR and their architectural partners at Skidmore, Owings & Merrill could break any skyline records, they had to solve a foundational physics problem that contradicted traditional skyscraper logic. To build a towering skyscraper in a place like New York City, crews dig down until they hit solid bedrock, physically anchoring the structure to the earth. Dubai doesn't have solid bedrock. Digging down only yields weak, porous limestone and deep sand. The solution was friction piles. In this cross-section, the tower relies on deep, vertical columns. Engineers drilled 192 piles 160 feet deep. As the massive concrete mat pushes down, friction between the rough piles and surrounding sand pushes back, locking it in place. With the ground secured, the tower began its vertical climb, introducing an invisible, high-altitude threat. When high-speed wind hits a flat, tall surface, it splits, creating miniature tornadoes on the opposite side, a destructive pulling phenomenon known as vortex shedding. To keep these wind rhythms from snapping the tower in half, lead structural engineer Bill Baker invented a system called the buttressed core. The building is shaped like a Y. When wind hits one of the wings, the other two wings, and the massive hexagonal center, absorb the push and pull forces. The exterior design takes this defense a step further. As the tower rises, the three wings step back at varying, uneven heights, creating a spiraling effect. Because the building's geometric shape is constantly changing, the wind currents break apart before they can ever organize into a dangerous rhythm. Engineers successfully turned the harsh environment against itself. They used the friction of the desert sand to hold up the massive weight and the asymmetry of the tower's geometry to tear the wind apart. Construction required a relentless vertical push, introducing an extreme logistical hurdle. Crews had to pump liquid concrete 1,900 feet into the sky before it hardened. Given a 30-minute travel time through the high-pressure steel lines, daytime desert heat would cure the concrete mid-pour, destroying the machinery. To buy time, pumps were run exclusively at night, mixing the concrete with ice instead of water to keep the temperature near freezing. But halfway through the build, the environment took a back seat to economics. The exterior cladding contractor went bankrupt, pausing facade work entirely. Shortly after, the 2008 global financial crisis wiped out real estate markets, freezing MR Properties' cash flow. Facing a ballooning $1.5 billion budget, the project was on the brink of failure. It was completed after a massive last-minute financial bailout from the neighboring Emirate of Abu Dhabi. In gratitude, the Burj Dubai was immediately renamed the Burj Khalifa, honoring Abu Dhabi's ruler. By 2009, the tower was ready for its final piece, a 4,000-ton steel spire. The problem was that no crane in existence could operate at that extreme altitude to lift the heavy steel onto the roof. The engineering crew bypassed the crane limit by building the spire entirely inside the hollow top floors of the building. Using a hydraulic strand jack system, they slowly pushed the massive steel pipe upward from the inside out, inch by inch, locking it into its permanent position above the clouds. Reaching the peak was an exercise in on-the-fly mechanical improvisation, fueled by immense financial force when the original plan collapsed. On January 4, 2010, the structure opened to the public. Making this vertical city functional required installing 57 of the fastest elevators in the world, including double-deck cabs that travel at an astounding 33 feet per second. The the tower also manages its own brutal microclimate. The heavy air conditioning systems draw out the intense Dubai humidity, producing over 15 million gallons of condensation every year. This water is collected and completely recycled to irrigate the massive landscaping and fountain networks at the tower's base. The sheer physical realities of the building border on the surreal. It holds 163 stories, features the highest outdoor observation deck on Earth, and stretches so far into the high-altitude atmosphere that the peak visibly sways up to 1.5 meters during a storm. Maintaining that scale requires a grueling, perpetual human effort. It takes a dedicated crew of 36 workers a full 3 months to manually clean the building's 26,000 glass panels. The day they finish, they lower to the bottom and start the cycle all over again. The Burj Khalifa operates as a working prototype for the absolute limits of human habitation. The structural systems invented to hold it up proved that if you manipulate geometry and friction precisely enough, even a patch of loose desert sand can support the impossible. If you enjoyed this breakdown of human engineering, hit the subscribe button and click the bell icon so you never miss a deep dive into the structures that shape our world.